In this video, we are going to discuss drawing larger Lewis structures, those with more than one carbon or potentially more than one central atom. So oftentimes in introductory organic chemistry, we will see a condensed formula such as this one. CH3NHCH3. And this formula here gives us a little bit of clues as to how to draw the larger Lewis structure. This methyl group CH3 is on the left side, there's an N in the middle, another methyl group on the right side, and so this implies that the CNC. So we have this initial structure for our Lewis structures, and these are all central atoms in this case, the carbon, the nitrogen in the middle, and the carbon. And the NH here tells us there is one H attached to the nitrogen, and 3 hydrogens next to this leftmost carbon tell us that there are 3 hydrogens attached here. Same thing with the rightmost carbon, 3 hydrogens. The last thing to do when drawing our Lewis structure is to make sure every every atom in general has a full octet. Hydrogens always want one bond, so every hydrogen I've drawn is satisfied. The carbons want 4 bonds, and we can see that the left carbon has 4 bonds and the right carbon has 4 bonds. The nitrogen wants 3 bonds and a lone pair, as we discussed as we've seen in the other Lewis structure videos. And so we have 3 bonds, we'll give it the lone pair. And so this is the proper Lewis structure for N-methyl-methylamine. What if we were presented with this condensed formula, CH3OH? Again, CH3 implies a methyl group. That's on one side, and then the OH would be on the right side. And the O, written directly adjacent to the H, implies the OH bond as shown here. And so we can fill in the 3 hydrogens around the carbon. We can establish that every atom has a full octet, or 1 bond for the hydrogens. Every hydrogen is good. This carbon has 4. This oxygen only has 2, and we know that it wants 2 bonds and 2 lone pairs normally, so we give it 2 lone pairs. This is the compound methanol. And here we see 2 central atoms. How about a compound listed like this, C4H10? This is just a hydrocarbon. There are no other atoms besides carbon and hydrogen, so carbon will always get to be the central atom. And in this case, we'll just assume that it is in a straight line. You will learn later on it's not always necessarily in a straight line, but in this case, we'll just draw a line of carbons and then surround them with hydrogens such that each carbon then has 4 bonds. So the first carbon on the left gets 3 hydrogens, 2 hydrogens for this middle carbon. Same thing for the second right middle carbon, and 3 hydrogens around the rightmost carbon. Are there 10 hydrogens? Well, we have 4 up on top, 4 on the bottom, 2 more makes 10. Every carbon has 4 bonds, every hydrogen has 1 bond. This is a good Lewis structure, and this compound is called butane. Okay, let's move on to another potential case. Here we might have a very simple chemical formula, CH2O. Now when we see something like this, we might think, well, how am I supposed to figure out what the central atom is? Well, generally carbon will always be a central atom. You'll never find carbon on the outside of the molecule, and so be safe to attach both hydrogens to this carbon. And the fact that it's written CH2 implies that those 2 hydrogens are indeed attached to the carbon. And since we can't attach anything else to those hydrogens, we put the O attached to the carbon. And now we need to ask ourselves, is every atom satisfied? Well, the hydrogens have 1 bond. Carbon only has 3, it wants 4. The oxygen has 1, it wants 2. And so we can oblige both the carbon and the oxygen by adding a second bond, a CO double bond. Now the carbon has 4 bonds, the oxygen has 2. If we draw on these lone pairs, it now has 2 lone pairs and 2 bonds. So this is a good molecule, or I'm sorry, a good Lewis structure representation of formaldehyde. often used as a preservative. Another formula we could look at, slightly expanding on formaldehyde's formula, C2H5OH. And again, this could be written any number of ways. We could write C2H6O, or we could write CH3OCH3. But let's look at this one first. We've written it in such a way to give you some clues as to how the atoms should be arranged in the Lewis structure. The OH is written like that. It's together. You should assume there's an OH group in the Lewis structure, so that there's an H attached to the oxygen. And C2H5 often will imply a group that looks like this. Here is C2H5. You see that 2 carbons are central atoms surrounded by hydrogens, and then we need an OH group, and so we can draw that. Filling in the lone pairs for the oxygen, we find that every central atom, the carbon, the second carbon, and the O, all have a full octet, and every hydrogen has 1 bond. Another way to draw this molecule, this is called ethanol. Another way to write it, CH3, CH2OH. So you may see that written, and that again implies the same Lewis structure. And you can see how this is even more clear. There's a few more hints here where we have a CH3 group, a CH2 group, and an OH group. And we can pick those out here, CH3, CH2, OH. Now, this is simply the chemical formula, one possible formula. It doesn't really tell us anything about the structure, so we won't look at drawing structures from this formula. But we could draw a different structure using this formula, CH3OCH3. And again, it's implying that there's a CH3 group, another CH3 group, and in the middle is an O. So we could draw this skeleton to start with. We know that O needs no more bonds, and we have 2 CH3s right here. If we give 2 lone pairs to the O, just like every other oxygen we've discussed, we now have a proper Lewis structure of dimethyl ether, which is a structural isomer of ethanol. And lastly, we could look at this structure, CH3COCH3. Again, we have several groups implied in this structural formula. 2 CH3 groups. Generally, we would assume that they are on the opposite sides of the molecule. And then we have a CO group. And this will often mean we have a CO double bond. So let's draw this with this structure here. I'll put a CO single bond for now. We may turn it into a double bond. Let's make sure we have the leftmost CH3 and the rightmost CH3. So now we have our 2, maybe we'll call this number 1, call this number 2. We have CH3 number 1 and CH3 number 2. And we have the CO group in the middle. And we notice that this carbon does not have a full octet yet. It only has 3 bonds. And this oxygen also does not have a full octet, even if I give it the customary 2 lone pairs. So if we draw a second bond between C and O, we now have a CO double bond, 4 bonds to this carbon in the middle, 2 bonds and 2 lone pairs to that oxygen.